So hello everyone. This is my talk, Deep Learning for Sentiment Analysis, in more detail using conv-nets for text classification. So just to give some context for you, who am I? My name is André Barbosa, and I'm an information assistant bachelor from University of São Paulo, and I'm a data, and I'm a data scientist at ILU7 and also an ML engineer there. And again, just to give some little bit more focus on what I do, ILU7 is a startup that sells, it's a marketplace that sells personalized products. And when I say personalized, I mean that we built a platform where people can sell their products. And when I mean their products is that those products were really made by them. They were handmade and crafted. And we truly believe that the effort, the passion that they. So as I said, ILU7 is a marketplace that people can sell their handmade and crafted products, and we truly believe that the effort, the passion that they put on it, makes those products really, really outstanding ones, really outstanding products. And as we are a marketplace, you can imagine that we usually tackle some challenges that comes from computer vision or natural language processing tasks. So giving more insight about it, so this is a picture of our software engineering team. And we believe in a really collaborative environment. And also we apply agile methodologies for software development. And we also have, like, because of this, we apply Scrum in our case. And every 2 weeks, we have what you call the sprint, and at the beginning of each sprint, we have what you call a hack day. So the hack day, what it is? Every team member has the freedom. We are free to study new stuff, study new technologies that we can think and strongly think that can bring some value to the company. So the purpose of this talk is one technique that I learned during those hack days, and so in this case, it's going to be like more a tutorial about deep learning, using deep learning, than a use case by itself. So as a member of the data science team, the stuff that we try to do every day, it's to do science. So when I say science, I don't want to mean like to reinvent the wheel or reinvent technologies or do stuff like that, but we usually read some research papers and see what's the real state of the art stuff that is going on outside, related to the companies or related to even academia, and we try to implement by our side. It's not like we do not try to replicate as it's the weaker one, because like research papers are really more complex than the real world applications. So in this case, I will go like to give some explanation about convolutional neural networks for text classification. And I reproduce some research papers. I use some research papers to base my arguments, but my implementation is somewhat simplistic one than the research papers that I did. I will give more details after in the end. So just to give some context of what kind of problems that we are trying to solve, let's say that you have a movie catalog, and those movie catalogs have some opinions from the users, and those opinions can be either positive or either negative. And okay, so for those who are familiar with machine learning problems, this is a usual sentiment analysis task. So we have some sentences. Those sentences are labeled as positive or labeled as negative. And the idea is that to build a model that generalizes a sentence for that. You give a new sentences. Those sentences you don't know the label, and the model tries to answer that for you. Okay? So for those who are familiar with deep learning, as it were discussed in the panel right here, the first kind of neural architecture that you might think that could switch well for this kind of problem are recurrent neural networks. And for those who are not familiar with recurrent neural nets, they are basically a kind of neural architecture that fits well for sequence of data. In this example, we have a sequence of shards, and it outputs a sequence of shards, but you also have like a sequence of words. And when I mean sequence of words, it could be a sentence. And again, it's a sentiment analysis task, and if you're using recurrent neural nets, you have the sequence of words. If you have the sequence of words, you have the context of your phrase, and if you have the context of your phrase, it might get some better results than a simple bag of words model, for example. However, there are some niches. First of all, recurrent neural nets are really, really hard to understand. And also they usually take a lot of time to train. And moreover, some recent research papers found out that other kind of architecture had been proven to be at least similar or even better than some RNN's applications. So as you guys can see right here, those are two different research papers. So this one is the first one, this one is the second one. And then here you have like for CNN, the F1 score, those are text classification tasks. And you have some different hyperparameters that were used. And the author got like 84%. And for the RNN, for like the same hyperparameters adjustments, he got like 83%. And so in this case, the CNN were better. And here we got like some different natural language processing tasks. Okay, so in some cases, the CNNs or convolutional neural nets, when compared to general recurrent units or LSTM, they got some better results sometime, like here, or at least similar, as you can see here, or even here. Okay, but first of all, let me introduce it. So what are convolutional neural networks? And why they are interesting and so forth. So the first stuff when you think about convolutional neural networks is that they combine the kernel filters that came from computer vision with regular neural nets. And so computer vision, we see an image. And computer doesn't see an image, it's computer see numbers. So in this example, you have like some image, and then you have a matrix of numbers that represents that image. And then the idea is that you have some convolution layers that performs the convolutional kernel filter. And then you have like those kind of functions are linear. You have some non-linear activation functions after that, like ReLU, for example. And then you have something like max pooling. And okay, let me show with more concrete example. So if you have like an image, you have some convolutions. Convolution, I mean like it's a window that convolves around the image. So it's go like here or here. And then you have some output. And then the output, you add some nonlinearity. When I mean nonlinearity, it's basically the ReLU or sigmoid or other kind of nonlinearity function for that. You have the max pooling, like here, and it's another layer on the convolutional neural nets. And in the end, you have the fully connected layers. What are the fully connected layers? They are basically the usual feed-forward neural nets architecture that you know. Okay, and after that, you have like some output, another kind of function like softmax to get the output predictions as well. Okay, so why they are so awesome? Why they make a lot of interest? They are so interesting because those convolutions, they learned by itself to take some features of your image based on the challenge that we are trying to solve. So this GIF is an awesome example. It was taken from a video uploaded on YouTube from researchers at Cornell University and NASA, one of the NASA laboratories. And they were trying to understand what the neural networks, what those convolutions layers were trying to learn, were learning by themselves, you know. So here in this example, this second convolution layer, actually, like I think it's just this neuron, it learned to detect the text given an image. So here you have the image, and it learned to see the text. It's not the best view of it, but it's not like it learned to detect if the image had some text or not, okay? However, I was talking about sentences, I was talking about words, and then I came and started about images to teach what are convolutional neural networks. So why and how those things are related? And the answer for that is word embeddings. That is, for those who are familiar with Word2Vec or Glove or other kind of embedding training algorithms. So those are basically representations of your words in a vector space. So now with embeddings, you have like some input, some words. Those words are mapped into a vector, and then you have a matrix. And if you have a matrix, you can convolve around that matrix and get some result that you would like to do for the problem that we're trying to solve. Okay, so now I will show some. This is the general architecture that I take it from the paper that I tried to implement by myself. I go step by step to explain with a little bit more details than this big picture, and then I come back for it. So first of all, the first thing that you have a sentence, like I like this movie very much, and you made a embedding lookup. So you just turn it into an embedding of word space. And then you have like windows. You can have windows of the same size and also windows of different sizes. So in this case, you have 2 windows of size 4, 2 windows of size 3, and 2 windows of size 2. And one really interesting stuff when you are applying convnets for this kind of problem is that when you are working with images, the windows can have like any width and any height. And here, the entire row represents, it is a vectorial representation of your words in the space. So the width of your window must be the same as your embedding input. And then what you vary here is the window height. And the window height is basically how many words are you slipping by, okay? Skipping by. And then you have some non-linearity activation function that turns into result in something like this, okay? And then you have the max pooling that, for example, in this case I'm using max pooling, it's keeping up the biggest value of this array. And then you have some flattening layer that combines everything. And again, here you have like the fully connected layer that performs the output for your prediction. So again, here is the big picture. You have the sentences, you have the convolution, the region sizes of your windows, the filters per window, activation function that goes right here, the max pooling right here, and right here. And then the flatten, you stuck everything together and make your predictions. Okay, so I will do like some live coding to give some more practical intuition about it. So the problem, again, that we're trying to solve is that we have some reviews from Rotten Tomatoes. So those reviews can be either positive or either negative. Like this one with the tomatoes are positive ones, and those one is this green stuff that I don't know what it is. It is a kind of negative. So, and again, another real intuition, real like good stuff, why to use convolutional neural networks is that, first of all, they are easier to understand than RNNs, so that's good. And they train really faster than when compared to RNNs. Are they intuitive when we talk about NLP tasks? No, but they work. So I will show some results. I will skip the next slide because I will show like by the Jupyter notebook that I will do right now. And if you guys would like to know further details about this topic, I based the paper that I read to implement this was from Yonkin. He's a Harvard PhD student. So the paper that he wrote was Convolutional Networks for Sentence Classification. And then Brits works at Google Brain. He has a blog post called WildML that tells some state-of-the-art techniques about deep learning and how CNNs. He has also an awesome blog post telling about how do CNNs had been proven to be used in different NLP tasks. So it's pretty interesting. And he's also has a tutorial for those who are like have some curiosity about the topic, about how do you implement a CNN for text classification in TensorFlow. Okay, so my implementation is different from his because I decided to focus more on the convolution layers, the layers itself of the code, because I thought that it would be more educational and people would understand it better. Okay, so here are some references that are, you cannot read it. right? Sorry. Okay, hyperlinks problems. Okay, so you can take a picture, but I will share my slide with you if you want it. And let's get some code. Okay. Does anyone can see it? Okay, I think so. I hope so. Okay. So here are some. I'll go like step by step. That I would like just to. Okay, let's start it. So some import functions and helpful functions that I got from the paper itself. So as you can see, I did a really simple pre-processing. So I just use a regular expression that I'm tokenizing stuff and clearing strings as well. I got a public data set for movie reviews from Rotten Tomatoes, and I concatenated those data into one single list of positive and negative examples. And both codes were taken from the Yongkin GitHub. Okay, so and these one were also taken from them, but I decided to modify it just a little bit because I changed the way that I iterate to my batch of data, right? So just running. So here the movie reviews from Rotten Tomatoes, we have like 5,000, around 5,000 positive reviews and 5,000 negative reviews. I just load them to confirm it, okay? And then I decided like to just check a little bit things up. So here is the first negative review. If I just do something like this, I'll get the first positive one. Okay, like you can see here, this categorical variable. And then I did some reprocessing. Neural nets, they don't understand words, they just understand numbers. Okay, and the idea here is just to build a map that I transfer from word to numbers. And every sentence from my reviews are padded with zeros until I get the maximum length of the review. So the maximum review size that I got here is 56, as you can see right here. And you can see, I think it's better. Okay, so if I just created it's mapped to 1, rock is mapped to 2, and so on and so forth. After the end of the sentence, I padded with zeros until the end of the whole sentence. And just to prove to you, so for example, this was the 0, it's 56, and with 1 is also 56, and it will happen for all of the data. And then I shuffle the data, okay, and did some train and validation test plate. I could do something more robust, like k-fold or something like that, but I just decided to do a more simpler and quicker paper implementation by my own. I just skipped that. And here is the CNN itself using TensorFlow. So here is the placeholder. So the sentence size is my input. And here the number of classes in this case of this problem are going to be 2, positive or negative. And I just used some keep-out probability to control overfitting. I will explain this further. Some unit tests that I did. So it's here. Okay, some unit tests that I did. And then okay, just will take a little bit to load. So what I'm doing here, I decided to use, as I said, I used the embeddings, and then the embeddings were basically those word representations. I didn't want to train my own. I didn't want to like just to prototype and give some quick development of it. And so I decided to use the Google News data set that were already pertained, and then I loaded into memory. Okay, so, and then I just keep the vocabulary that I would use. Okay, and if I have some word in my vocab that does not exist on the Google News one, I just randomize it. Okay, so here's basically what I'm doing. And then I go for the architecture that I show you in the slides. Okay, so this is still loading. I will try to explain why I'm doing it is still loading in the memory. Okay, so I do the embedding creation. The embedding creation is basically doing the embedding lookup based on the input. The input is your extensor that could be like in this case, it's your sentence size, the vocab size. So it's basically doing this processing here. Okay. And then I have the convolution layer. In this case, I built both the convolution layer. I go like some really quick, but please, if you would like to know a little bit more, it's available on my GitHub. So it's basically convolving around the embedding. You add some nonlinearity, and then you have the output, this convolution output, and then I perform the max pooling in the end. So it is basically considering just one window. Okay, so for applying all the windows, I have these different filters. Okay, it's basically doing the same thing, applying everything. Let me just right here and right here. Okay, apply filters. Okay, and then I have the flattening layer that, as I said, concatenate every stuff together. And after all, this is the flattening layer. So it's basically concatenate everything. And after all, I have the output layer that basically performs the convolutional neural network, as you know. So it's basically matrix-wise multiplication. You have the weights, you have your input. So I think it's pretty straightforward to understand that part. Okay, so I decided to keep some laws from the weights and from the bias to apply regularization. And I will explain why in a second. So here's the convolution, as I said. So here I have the vocab size, the embedding dimension. I created the embedding layer. And the filter that I decided to apply here, it's that you have three windows of size 128 windows of size 3, 128 windows of size 4, and 128 windows of size 5. And the flattening layer, the dropout, the number of classes you create right here. Here are the construction of the neural net itself. Okay, and the training process, some statistics that I did from training and validation. And I decided to train just in a single batch just to show to you how quick it trains. So let's check. Okay, so as you guys can see right here, it trained really quick, but you have some differences like from the training, from the validation stats. And for that reason, I decide like to use some regularization parameters, as I said before. So here's the training, and I will not train it here because it took around an hour on my CPU to train everything, but just to prove for you, I got some 79%, while the paper that I tried, I based it myself, use it around 80%, 81%. So just keep it training here just to show for you, and that's it. Okay, that's it.
I think we have time for about 3 questions.
Hi, you're doing sentiment analysis, right?
I just for this test.
Okay. You're using neural network for text classification. Neural network have a fixed amount of input data. How do you deal with multiple length of data? Because you're taking each word and padding at the end, so you're putting zeros, but you're basically limiting the size of the word and the number of the words you want to put in. There's another way. Do you know another way to encode your text so you can use arbitrary length of words and arbitrary length of each word on a neural network?
In this case, I actually don't know, because I think like when you are dealing with convolutional neural networks for image classification, and that's kind of thing that I study at level 7, for example, we usually work with fixed size of the data. So the image would have like the fixed size of height or width, for example. So it's basically the same process for words or syntax words. It answers your question?
Yeah, when you use images, you do a pre-processing of the images and reduce it to a fixed, right? Or upscaling the image. But on text,
it's basically the same thing. Like the input of my neural network will be the sequence, and everything. So every sequence will have the same size. So if you crop the image to get it some size, to fix the size that you input into your image, you are losing some data, right? And then if I just pad it with zeros, I'm adding some data, but the data even will not be mapped to my dictionary. So I think it's not a problem with that.
Okay, I think we have time for one more.
How do you find the best architecture for a convnet?
I copied from the paper just for the implementation. Like I based everything on the paper itself just to learn it and then to apply for a real world situation. And for this first time, I decided just to keep the same architecture. Okay, so as I'm like going to improve it, I would keep the same architecture because it fits well for this kind
You
of
tried to add more layers? Or?
Actually, I just changed a little bit of parameters. So I didn't change the architecture itself. But some stuff that I changed from my network from the real paper stuff is that, first of all, this probability, I decided to, it was just trial and error that I found the best results. And the weight initialization. So here, as you can see, you cannot see. Here. So I decided to use like a random array that goes from minus 0.25 until minus 0.25. And if you see like something. I erased that. No, here. I first tried with -1 until +1. So I saw that this one worked better. So for this reason, okay. So this answer you or okay?
Okay, thank you. Thank you, Andre.